Uno, dos, tres, cuatro.
Hi everyone. Today we're going to take a look at infinite geometric series. Studying anything around infinity is actually usually one of my favorite things to take a look at in high school math. If you wanted to look up something interesting after, you should look up this guy named George Cantor. And he studied different types of infinity and different levels of infinity. I think it'd be something very interesting where you might want to be able to learn about that there's more than one type of infinity. Anyways, here's an infinite geometric series. So here's a scenario. We have a 1 meter long table, and we'll draw this something like this. Here's 1 meter. And the grasshopper is able to jump halfway to the end of the table right here. And after that, each time he can keep jumping, and he jumps halfway to the remaining end of the meter, end of the table. And so his next jump, he is now all the way at 0.75 meters. He's 3/4 of the way there. And then he keeps jumping and jumping and jumping. And what ends up happening is he's going to keep jumping and jumping, but even after the 100th jump, he won't quite be at 1 meter. He's going to be very, very, very close to 1 meter, 0.9999 something, but he won't be quite at 1 meter. And after the 1000th jump, he still won't be able to be quite at that 1 meter end of the table, because he's still halfway towards the end goal right there. And so it creates this paradox. And what we have is we have this idea of being able to figure out, well, what is an infinite geometric series? And an infinite geometric series means that sometimes you could have an infinite number of terms and essentially approach a number. Okay, so what do we mean by that? In the case of the grasshopper, if he jumps half a meter for that very first time, then the next time he's going to jump 1/4 of a meter, and then he's going to jump half of that, so 1/8, and then 1/16. And he's going to keep doing that all the way for all of his jumps. He's going to half them. So his jumps get very small until they're essentially zero, but he's still moving technically a tiny bit. And if you add up all of those numbers, say just for the first 9 terms, you're going to get something that's going to be so close to the number 1, but it won't quite be 1. Now remember, those were the individual jumps, but if you take the S of n of it and you find what their total sum is, and I'm going to do this pretty quickly, but if you were to add a half and 1/4, you would get 3/4. And if you're to add another 1/8 to that, you're going to get 7/8. And what you're going to find is this pattern that emerges, where it's basically going to be just under 1. But even if you add more and more terms, you won't reach 1, and you'll never reach 1. And so by the time you've done 9 jumps, you've jumped 511 out of the 512th of a meter. And that's so close to a meter, and you just want to say it's 1 meter, but it's not 1 meter. So this type of series is part of an infinite geometric series, because we could do this for an infinite number of terms, and the ... here tells us that it's going to keep going and going and going. And it's something that's called being convergent. And convergent just means that the sum is getting closer and closer and closer, rather than farther and farther and farther. And in this case, we're saying that the sum will never actually reach 1, but we can say it will essentially just about equal 1. It's very similar to that concept of studying asymptotes from pre-calc 11, where you get so close to being able to say, hey, we are approaching this value, we just don't quite get there. So here's your first question. Say you have something like this. You have the sum of 10, 5, 2.5, 1.25, 0.625. If you were to add that up forever, what would you basically get to? What would you almost be at? And so you could take your calculator and you could say this, okay, well, 10 plus 5 is 15, 15 plus 2.5, 17.5, add another 1.25 to that, 18.75, add 18.75 plus 0.625, you get 19.375. You can add would that be 0.3125? You get 19.6875, and you could keep adding these little bits, and you're going to get closer and closer and closer to the number 20, but it's not going to quite be there. So you could say something like this: you're going to be at, we could say here you're at approximately 20, and that would happen if you kept adding that up over and over and over again. But we could do that where we could say, in this case, there's 1, 2, 3, 4, 5. We only added up 6 terms for what we did, and we got pretty close to 20. But we could have added up 100 terms, and we'd still be pretty close to 20. So we can say it's essentially the number 20 if I add up those terms forever. So we're able to do something for an example like that, but why would it be difficult to do something for something like 1, 2, 4, 8, 16, blah, blah, blah. So now, if you think back to your grasshopper, instead of your grasshopper's jumps getting smaller and getting close to that end of the table, now your grasshopper jumps are getting out of control. You went from 1 to 2 to 4 to 8 to 16. Then the grasshopper's jumping 32 meters and 64 meters, 128 meters, and soon they're jumping thousands and thousands of meters and kilometers. And so basically, this is an example of something that isn't converging. Your common ratio is 2. And when your common ratio reaches something where your jumps get progressively bigger and bigger, you have something called a diverging series. And something like that can't be calculated because essentially you could say this like, I don't know, maybe the best way to say it is this can't be trapped, or it gets out of control. Okay, so what we're going to say is this. Therefore, we can calculate a convergent infinite geometric series, but we can't calculate the sum of a divergent infinite geometric series. And if you want to know how do we know if something's converging or diverging, you could say something's converging if the values are getting smaller. So if you could say if each successive value gets smaller, but that's actually not the best definition because we haven't taken into account positives or negatives or anything like that. And so what we do want to say is it would be if our common ratio is something where if it's a positive number, it's less than 1, and if it's a negative number, it's between -1 and 0. And so what you could say is if your common ratio is something between -1 and 1, then we could say you would have something that would converge. Having a common ratio of 0, I think that would be another discussion. But basically, if you have a common ratio of 0, then I would say that would create a unique type of series like we saw a couple classes ago. So we're going to say our common ratio, if it's defined between -1 and 1, then it's going to be converging. And then you could have an infinite number of terms to be able to calculate what the sum of the series is. Now, let's think about what would happen in our formula if you had something like this with a common ratio between -1 and 1. So let's take the idea of, for example, having something where our common ratio is 1/2. And if you're going to use your geometric series to be able to calculate something, to be able to find out what would happen for an infinite number of terms, let's think about what that would look like. So here, what you could almost say is you could say, well, S of infinity, we have an infinite number of terms. And if that's going to equal something where I have A times 1 minus, well, in this case, we're going to say this is like, we said it was 1/2, and it's going to be raised to the power of n, where n is the number of terms. So we're going to say that that is an infinite number of terms. What would happen to this 1/2 to the power of infinity? And so if you take 1/2 and you say 1/2 times 1/2 times 1/2 times 1/2, well, you're going to get something that's going to be the same as saying, that'd be the same as saying 1 over 2 to the power of infinity, which would be 1 over some sort of massive number. And having 1 over some sort of massive value is essentially the same as saying 0. And so if you have something like that, that means that this value is basically all for nothing. It goes away. And you'd be left with something that would say 1 minus 0, which is 1, and you'd be left just with the value a on your numerator in this formula. And so from there, we could say that we can create an infinite geometric series formula of just saying it's going to be a over 1 minus r. Okay, that's going to be our sum. And so that is given to us right here. You can look at it in terms of sigma here if you want as well. Okay, so now when we look back to those previous questions, and let's go back here where we said, how about example 1, where this is basically saying it's 20. Well, what would happen if you had something like S equals A over 1 minus R? You could say S of infinity is going to equal your A value, which is 10, over 1 minus your common ratio, which is 1/2. And if you do 10 divided by 1/2, you get 20. Okay, so everything checks out. Okay, so let's take a look at a couple examples here. It says calculate the sum where the sum exists. And so we have a couple examples here. And in some cases, we could find the answer. In some cases, we can't. But in order to do that, we need to know, well, what's our common ratio for each of these? Because if our common ratio is something bigger than 1, then we know that we would have something that would be diverging. And if it's diverging, then we can't find its sum because it would be out of control. And so something like this would have a common ratio of -1 divided by 5, -1/5. This would have a common ratio of -9 over 15, which is the same as saying -3 over 5. Part C would have a common ratio of, this is getting bigger. We're timesing it by 10 each time. If you were to take this value and divide it by this, you would get a common ratio of 10, and that means that would be diverging, which means you can't calculate its sum, so you're done with the question. It can't be calculated. It would just get out of control and reach infinity. And then for part D right here, you could say this would be √3 over 3 would be its common ratio right there. So for each of these three, you would be able to calculate its sum. So why don't you try this right now? We have a pretty straightforward formula of S equals A over 1 minus R. So why don't you pause the video right now and find out the sum for A, B, and D. Okay, you may have left it as decimals or fractions. Taking a look at part A, you should get 25 over 6, part B, 75 over 8, and part C, depending if you rationalize the denominator or didn't rationalize the denominator, you could get 9 over 3 minus √3 or 9 plus 3 root 3 over 2. Both are totally acceptable. If you do have decimals, remember you could always take your decimals if it's a rational number, and using your graphing calculator, you could press math, enter, enter, and then that should be able to convert it into a fraction form. So those are your three answers. Okay, find the sum of the infinite geometric series for our next question right here. And let's start by finding our common ratio. Our common ratio is going to be -2 over 5. Find the common ratio of the numerator and find the common ratio of the denominator. So then, given that, we could say s of infinity is going to be equal to a, our first term, over our common ratio, which is -2/5, and then we should be able to just plug that in and be able to get an answer pretty quickly. So you could say 2/5 divided by 1 plus 2/5, and that should turn into something that's going to equal 2 over 7. Just know that those can be added together if you're doing everything manually right there, and that would have equaled 2/5 over 7 over 5, and then you could times by the reciprocal, and that's how you end up with 2 over 7. Okay, for our next question right here, we have an infinite sigma question. Again, no new tricks here. We know that if you take this 2, you could plug that in there and you could list the first few terms. So let's do that. If you plug a 2 in there, then you get something raised 2 minus 1 to the power of 1. So your first term is going to say 8 times -1/2 to the power of 1. And then your next term would say 8 times -1/2 to the power of 2, and then 8 times -1/2 to the power of 3. And if you want to figure out what all of that can simplify to, you would get here, this would be -4, and then right here, this is going to be +2, and that's going to be -1. ... Okay, so yeah, given something like this and having an infinite sum, you could say S equals A over 1 minus R. Your first term is -4, and your common ratio, it's kind of messy here, let's rewrite that. Your first term here is -4, and your common ratio is -1/2. So then based off of that, you could change those to pluses. It'd be the same as saying -4 over, let's clean this up a little bit. 1 plus 1/2 would be like saying 3 over 2 eventually. And then you times that by the reciprocal, and you would end up with something that's going to be -8 over 3. And that would be our sum for that question. That's a bit of a tough one because you have positives and negatives. So you're going from -4 to +2 to -1 to +1/2, and going back and forth between positives and negatives. Sometimes it's harder to see what the total sum is going to become. Okay, a couple word problems. So you have a pendulum that swings and has an arc length of 25 centimeters, and in each successive swing, you lessen it by 5%. So take a look at what they're saying. They're saying it lessens by 5%, but that means it retains 95%. And they're saying when the pendulum stops, what's the total length that the pendulum will have swung? And so you could say, well, I guess that's a way of saying that's going to swing forever. It's going to keep going back and forth. There's no set number of terms there. There's an infinite number of terms. But we could say that our first swing is 25 centimeters, and then our common ratio is going to be 95%, 5% less than 100%. So we can say our common ratio will be 0.95. And if you put that into your calculator, you would get something that's going to give you 500. And so based off of that, you could say the total amount that it's going to swing is 500 centimeters. Okay, I know last class I think we talked about a ball dropping from a truck or something like that. You could say if a ball is dropped from 12 feet and it rebounds to 2/3 of the distance from which it fell from, find the total distance that the ball will travel. And then sometimes you'll hear this term, it'll say until it comes to rest. So it's the same scenario where we have to look at our up and our down bounce because that's the total vertical distance it's going to travel. And we had this idea of saying whatever you find, you want to times it by 2 to get the up bounce and the down bounce. But then in this case, you have to subtract 12 because your first bounce only has the down bounce and it doesn't have an up bounce. So you can't double count that part right there. Okay, so given something like that, we could say our first term is 12 and our common ratio is 2/3. And then we need to double our answer to get the up and down bounce, but we can't double count this. So we have to subtract the 12 from right there. And so if you do something like that, you would say 12 divided by 1/3, that should give you 36, I think. So 36 times 2 is 72 minus 12. All of this should equal something like 60 feet. So actually, I would say for the actual computational part of this, using the infinite geometric series formula is going to be easier than using the geometric series formula. Now for something like a question like this, and this is kind of weird, 0.24 repeated. Take a look at something like this. If you had, if you said something like 0.2, and then you type in a ton of 4s. Let's see, I just got to change my format here. There we go. If you take something like this, I'm just gonna make this a little bit smaller so you guys can see this. If you take something like that and you just go 4, 4, 4, 4, 4, 4, 4 like that over and over and over, and you press enter, enter. Whoops, I probably didn't press enough 4s. If you go 0.2 and you just press all of these 4s, apparently I need more 4s. And you press math, enter, enter. Then you're going to get something in which it actually will convert it to a fraction, and it'll say that you have 11/45, and that's what we're looking for this particular question. So what does that mean? Like, what would we be able to say for something like this? 0.2 is separate from the rest of this. And we're saying we had the 4s are going to repeat. So from there, you're going to have a 4 there, and then a 4 here, and then a 4 here, and so on. And so as they continue to repeat, they want to know what would be the sum of this plus this 0.2 that we have right here. Now, of course, we've done our gimmicky way by putting it in the calculator and getting 11/45. But what we could also say is we could do something like this. We could say, well, 0.2 we're going to leave for a second here. But I can find the infinite sum of this part by saying it's going to equal my A value over 1 minus my common ratio. And if I calculate something like that, let's see what we get. 0.04 divided by you get 2/45. And then for this 0.2 part, if I take that and I add 2/10, or you could actually say, instead of saying 0.2, if I wrote that as 1/5, and I get some sort of common denominator, so I could times this by 9, and then times this by 9, then I would get 2 over 45 plus 9 over 45, and that is going to add up to 11 over 45. Okay, definitely a weird question. You probably hear me in class saying this is going to be some sort of omit. I'm not sure if we're going to look for something quite like this, just because there's such a gimmicky way that you can get the answer in your graphing calculator. I'm not sure what it fully shows us, but anyways, we could talk about it a little bit more in class. Okay, you have one last example here, and for sure for this example, I would say we would need to do some heavy trig review to be able to say that we're okay to move ahead with this. So I think because this is the first unit that we're taking a look at, it's something where it'd be challenging to be able to give you guys a question like this, given that you haven't looked at trig for a little bit. But at the end of the year, when you're doing some year-end review, it's a good question to be able to have a chance to revisit. So I'll take you through it right now, but use it just more for enjoyment or curiosity. But until I feel that we're ready to be able to assess trig, then I wouldn't be super concerned about something like this. If we take some values and we take values for k and you put them in here, then our first few terms would say this. If I put in a 1 for k, then I'd have tan x to the power of 0. And tan x to the power of 0 would be followed by tan x to the power of 1, tan x to the power of 2, and so on. And we know that, I should actually say that it's this. Tan x to the power of 0 is the same as saying the number 1. So I have 1 plus tan x plus tan x squared. Every time I go from one term to the next term, I'm timesing it by a tan x. In other words, my common ratio is going to be tan x. And so based off of that, if you have an infinite number of terms, which they're saying we do, then we could say our first term is 1, and our common ratio is tan x. And they're saying when you do all of this, it's equal to the number 1. So in other words, this 1 over 1 minus tan x that we have right here is going to be equal to 1. So from there, are we able to solve for tan x and look at all answers for x between 0 and 45 degrees? So this 1 minus tan x, we want to multiply to the other side here. So let's times both sides by 1 minus tan x and times this by 1 minus tan x. And we would get something here that would say 1 subtract tan x is equal to 1. And then if you do some algebra here, you could say tan x is going to be equal to 0. And if that's the case, when does tan x equal 0? Well, tan x equals 0, and this is probably going to say, like, a lot of you are going to say, I have no idea when tan x equals 0. You may have looked at some quadrantal angles in the past, and if you have something like that, you know that tan is equal to your y over x ratio, or sine over cosine. And if you have something like that, you would have values in which you would get an answer of 0 here and here, because y over x would be 0 over 1, which would equal 0, or 0 over negative 1, which would equal 0. And so that happens at 0 degrees and at 180 degrees when you move around a unit circle. But if they want to know all the answers between 0 and 45 degrees, we reject the 180 and it would just be at 0 degrees. And my guess is you would say, I do not remember any of that from last year, and we can talk about it some more in class. So I wouldn't worry too much. I think you see that again on example 5, question 5C. So we'll probably have to talk about that maybe a little bit more. Yeah, I wouldn't worry about that too much. So anyways, here are some questions to practice, and we can discuss that more in class. Thanks.